Welcome to this explainer. I'm absolutely thrilled to have you here today because we're taking a step-by-step journey through a really cool part of grade 7 math, linear functions. If you've ever wondered how long you actually have to work to afford a new phone or a video game, well, you're in the right place. We're going to connect real life to math by using tables, graphs, and equations. It's going to be clear, it's going to be highly visual, and honestly, it's going to make a ton of sense. So let's get into it.
Here's our roadmap for today. First, setting up the problem. Then, moving from a table to a graph. Finding the equation, comparing proportional versus non-proportional relationships, and finally, a quick student self-check to make sure we've got it down. Section 1. Setting up the problem. Let's ground our math right in reality.
To kick things off, we're using a perfect real-world scenario from our source materials. Imagine you've been hired by your neighbors to babysit their kids on a Friday night, and you're being paid exactly $8 per hour. Now, hopefully the kids are little angels, because otherwise you should definitely be asking for a raise. But for now, this is our baseline. That $8 per hour, that's what we call our unit rate. For every single unit of time, which in this case is 1 hour, you earn exactly $8. Keep that number locked in your mind because it is literally the star of our show today. Okay, so to make sense of this, let's build a simple input-output table. For our input, we have our X value representing hours worked, and for our output, we have our Y value representing earnings in dollars. It's super straightforward. If you work 1 hour, you just multiply 1 by our $8 rate, which gives you $8. Work 2 hours, well, 2 times 8 is 16. Work 4 hours, 4 times 8 gives you $32. We're seeing a really consistent pattern here, right? Every single measure of time is multiplied by the exact same constant number to figure out your pay.
Section 2. From table to graph. Let's take those numbers and actually visualize them.
So how do we take all that table data and build it out visually on a coordinate grid? The steps are beautifully simple. First, you just pair your table's X and Y values together to create coordinates. That means 1 hour and $8 becomes the ordered pair 1, 8. 2 hours and $16 becomes 2, 16. Next, you just plot those points on your grid. And finally, you connect the dots. Because our rate is completely constant, when you connect these points, you're going to get a perfectly straight line.
Now here's a really interesting spot, the point 0, 0, which we call the origin. Why does our line start right there? Well, think about the real world for a second. If you work 0 hours babysitting, your neighbors are going to pay you exactly $0. This right here is the absolute hallmark of a proportional relationship. The graph of a proportional relationship is always a straight line that passes right through the origin. Simply put, you don't work, you don't get paid.
And this brings us to a brilliantly clear way to spot a major grade 7 math standard, finding the unit rate visually. If you look at where the x-axis equals exactly 1 and follow that straight up to our line, the y value is exactly 8. This point, 1, r, where r is our rate, visually proves that for 1 hour of work, you get $8. It's so cool because the graph and the table are telling us the exact same story, they're just using different languages to do it.
Section 3. Finding the equation. It's time to summarize everything we've found so far.
The crucial next step is figuring out how to compress all of that table data and graphing work into a single, simple mathematical rule. To do that, we need to introduce a new vocabulary word, slope. Basically, slope is just the measure of the steepness of a line on a graph, and it shows us a constant rate of change. And here is the magic connection for this lesson. In a proportional relationship, the slope is exactly the same thing as the unit rate. Since our unit rate is $8 an hour, the slope of our line is also 8. Every time we move over 1 hour on the graph, we move up exactly $8.
Which brings us to the whole shebang, our final equation for this scenario, y equals 8x. It is incredibly satisfying to arrive here, isn't it? Y, your total earnings, is always equal to 8 times x, your hours worked. This is that classic y equals kx format of a proportional relationship, where k stands for our constant of proportionality. And in this case, that's our unit rate of 8.
But hold on, before we celebrate too much, we always need to perform a reasonableness check. This is such a vital habit in mathematics. We've got our abstract equation y equals 8x. Let's test it out. If you substitute 10 in for x, meaning you babysat for a pretty grueling 10 hours, the equation says y equals 8 times 10, which gives us $80. So does earning $80 for 10 hours of work make sense at a rate of $8 an hour? Yes, it absolutely does. The math completely checks out with reality.
Section 4. Proportional versus non-proportional. What happens when the rules change just a little bit?
Let's slightly tweak our scenario. What if your neighbors are just incredibly generous and they decide to hand you a $10 flat tip the moment you walk in, plus your normal $8 an hour? In our original proportional setup, we had y equals 8x, starting right at 0, 0. But contrast that with this new scenario, y equals 8x plus 10. Because you get that $10 just for walking through the door at 0 hours, your starting value on the graph actually shifts up to a y-intercept of 10. This is what we call a non-proportional linear relationship. It's still a perfectly straight line, it still has a constant slope of 8, but because it doesn't pass through the origin anymore, it is no longer proportional. You'll definitely see a lot more of this y equals mx plus b format in Algebra 1, but for grade 7, the big takeaway is just recognizing that a starting value shifts the line right off the origin.
Section 5. Student Self-Check. All right, now it is your turn to apply these concepts.
Let's wrap up this explainer by having you apply this same guided journey to a brand new scenario taken straight from our source materials. Imagine a taxi that charges exactly $2 per mile with absolutely no starting fee. Think through the exact steps we just took together. How would you build the table for this? What would the graph look like? And most importantly, what would the linear equation be? Take a quick mental second to map it all out.
Okay, let's see how you did. For the table, your input is miles and your output is cost. So 1 mile is $2, 2 miles is $4, and so on. For the graph, because there's no starting fee at all, 0 miles costs $0. That means our straight line goes perfectly through the origin, proving for sure that it's a proportional relationship. And if you look at where x is 1, the y value is 2, which reveals our unit rate perfectly. Finally, putting the whole puzzle together, the equation is simply y equals 2x. The total cost y equals $2 times every mile x. If you got that, you have beautifully grasped the core of this entire lesson.
I want to leave you with one final thought to mull over based on what we just learned. If you sit down in that exact same taxi, but the driver suddenly tells you there's a $4 flat starting fee before you even drive a single mile, how would that physically change the starting point of your graph? And what happens to our tidy little equation? I'll let you think about how that shifts our beautiful proportional line into a non-proportional one. Thank you so much for joining me on this explainer. Keep asking great questions, and I will see you next time.